Hi everyone, Dr. Matthew Michael here from NJIT. I'm going to continue on my explanations for Chapter 5 for differential equations, talking about series and how they affect differential equations. Once again, I'm going to enlist the aid of another person's PowerPoint because I like how they describe this. So, here we go. Let's take a look at this. So, last time we talked about the Euler equations. We classified our singular points. And we talked about that if they had a specific form, x squared y double prime plus alpha x y prime plus beta y is equal to 0, we could get it to work. We could get our solutions to have a specific form, y is equal to x to the r. Great. But as I mentioned, that doesn't always happen, but we can use Euler type equations to help solve it. So first, go back to the source. Recall that x naught is equal to 0. Let's say that's equal to a regular singular point of our differential equation, big P of x, y double prime, plus big Q of x, y prime, plus r of x, y is equal to 0. Now, last time, we classified it as a regular point if we could get our q of x over p of x, or little p of x, times x, and make that linear, that limit go to a finite number. And the same thing with r of x over p of x, but with x squared. In both of these cases, x little p and x squared little q, both of their limits were finite numbers. So because of that, we can use that to help form the basis for what will become known as the method of Frobenius. We're going to talk about it in its most simplistic form. It's 5.6 if you want it in its more special cases form. Take a look at the later sections of this chapter, but I'm not going to be doing videos about that because it can be confusing, and I want you to focus on what we'll be covering on the exam. So, when we divide out by little p of x, big P of x, we get y double prime plus little y double prime plus little p y prime plus little q y. If we multiply it by x squared and group carefully, we'll notice that we'll get an Euler type equation. See, x squared y double prime plus x beta, x squared plus x squared y double prime plus alpha x y prime plus beta y is equal to 0. And frequently, since we're using polynomials as our p and our q's, we can either Taylor expand, or it'll be in a ready-made form already in this form. And so if we expand those xp's and x squared q's fully, we will frequently see the pattern emerge here. And if we use p naught and q naught, you'll be surprised how often that will help us create a nice solution for our Euler type of solutions. That frequently our higher order terms, p1, p2, p3 on, and q1, q2 on, will frequently cancel out. And if that case does happen, in the case of Euler equations, we literally have just an Euler equation. Even if it doesn't, frequently we can get a lot of information from the Euler equation, or the Euler equation form of our differential equation. And in those cases, we assume that that r that we obtained from the Euler type equation can be multiplied by the solution type that we did before, the series solution a n x to the n. And we just multiply the x to the r, that smoothing over effect, and multiply it times our normal series, put them together, and we get a solution type. Now, this should sound like that. It sounds like it would be a lot of work, right? Yeah, your intuition was correct. So we're only going to be covering over one example of this in the PowerPoint. If you have questions, please come to my office hours if you're taking a class with me. If not, leave questions down below and into YouTube comment land. I will try to answer your questions or create another video describing how we can deal with that. So let's take a look at solving one of these. So 13 slides to answer one question. So 2x squared y double prime minus xy prime plus 1 minus x. Notice if I divide out by 2, I get something similar. I get an alpha value of 1/2 and a not quite sure value for our beta value. So, do normal ways. Let's do our different limits. Limit as x goes to 0 of x times r. Set up our big Q of x over p of x. So that becomes limit as x times negative x over 2x squared. The x is all canceled out. I'm just left with a negative 1/2. Notice that should sound very familiar from what we see here from my alpha value. Notice in the second case, my limit is x squared times my big R of x over my big P of x. So that becomes, the x squareds cancel out, and I'm left with 1 plus x over 2. The x goes to 0, so I just let that become 1/2. Notice that that's if I ignore this x right here, and in that case I have x squared y double prime minus x over 2y prime plus 1/2 y, my cursor disappeared, is equal to 0. In that case, that other equation is going to pop up later. But because both of these limits indeed are finite, we can kind of regularize your series solution. So it gives you a couple of points. So for any values, for any terms in the series beyond P1 and Q2, it's equal to 0. So let's take a look at our characteristic equation. So I have, I end up getting a characteristic equation that can be factored out as 2r minus 1. R minus 1 is equal to 0. So r is equal to 1/2 and 1. Fancy, fancy. Those values will be important later. So, remember, if I multiply a term on the outside of the series, so I have series an x to the n, as n goes from 0 to infinity, and on the front I have my x to the r. Move the x to the r inside, and I'm going to get x to the n plus r, or x to the r plus 1, r plus n. Take your derivatives. Notice nothing cancels out nice and pretty like we did before, because there's no n minus 1 terms. R is hanging out to play. Plug that into our equation that we see up at the very top up here. So you get 2x squared y double prime. So 2x squared times this. The x squareds cancel out with a negative 2. So I just get n, r plus n minus 1, x to the r plus n. Next term is minus xy prime. So minus x times this. This 1 for the exponent from the x cancels out with this one. So once again, I'm just left with an, r plus n, x to the r plus n. Now that nasty 1 plus x is just like the 1, and we want the x to go bye-bye. Unfortunately, it doesn't. So we break the 1 and the x apart, multiply them separately to 2 different series. Unfortunately, in order to combine our sums the way we want to, I'm going to have to re-index the last series. When I do that, now I have the bottom term here as n is equal to 1 to infinity instead of zeros to infinity. So in order to deal with that, I'm going to pull out the first term out of each one of my earlier series. And when I pull out those a naught terms, a0 terms, look who shows up but our best friend, the characteristic equation that we had earlier from our other type thing. It has a special name now. And once I only have 1s down in my limits, 1 to infinity, now I can make my lovely recurrence relation, and I have 2 equations. I have my characteristic type, and I have my recurrence type. Now, since we're no longer dealing with just Euler, it has a very special term, the indicinal equation. And like I said before, it refers back to its Euler equation type characteristic solution, and those R values are very important. It's very easily just to solve for those R values in your characteristic type equation, and those will be your important R's, your x to the R plus m. You can solve later. In this case, we've already solved them. They're 1 and 1/2. You remember? Those numbers are special, and we call them the exponents of the singularity, because those exponents help smooth that singularity over, except for if that x value is equal to 0. We still can't plug in 0, but every other value will work. So, the exponent, that's the singularity, determine the qualitative behavior of the solution near that regular singular point. So, recall that in that case, we plug in x is equal to, r is equal to 1 or 1/2. We can cancel out that first term. But if we focus on the recurrence relation, we can once again solve for our ANs, our coefficients. So, solve for that. I can complete the square nicely enough, and I have a recurrence relation when r is equal to 1 and r is equal to 1/2. And we'll have to do these recurrence relations separately. Notice the difference in the in our indexes an and an minus 1. And when so that's just a difference of 1, thankfully, because that helps form a then notice a0 will be in all of our solutions for a1, 2, 3, 4, 5, and on. As you see here, 0, 0, 0, 0. We notice that alternating series is popping up again. So we have -1 to the n in our pattern right here. Notice in each of these that we have the forming of a factorial, as well as we're multiplying by the prime, not the prime, it's the odd terms. So 3, 5, 7, 9, 11, and on, and on, and on. So we have a nice little thing. There are other things that we could do to make our thing even simpler. If my estimates hold, I'm not sure. But there are ways that you could simplify this. I need to double check, but there are other ways that you could simplify this. But we do have a pattern, and the pattern is good enough. So when when my r is equal to 1, I have a series solution like so. I plug in my current solution here, this here, because notice this term in the series only works for n greater than or equal to 1. Pull up the a0. So there's an a0 here, so factor out a0 x to the 1, and I get a nice pretty term here. Nice pretty term. So I have now solved one part of the equation. The other part, that r is equal to 1/2. So plug that 1/2 in, we get a slightly different recursion. We plug that in though, we still get factorial, we still have an a0, we still have an alternating series. We're just not quite making it all the way up. It's to the 2n minus 1, whereas if you noticed before it was 2n plus 1. So different odd terms. Instead of it being 3, 5, 7, it's 1, 3, 5. Slightly smaller. I hope you notice this. If you don't, please leave a comment down below and I will explain it in a future video. But notice in both of these cases I can do the ratio test to show that their radii of convergence is infinite. That the ratio test gives a a row value of 0, much so therefore I have an infinite radius of convergence. So it will converge for all values of x, except don't forget that I can't plug in x is equal to 0 because I have a singularity. I don't like that. Even though this works this way, just be on the safe side. So I now have two solutions. So my general solution is c1y1 plus c2y2, just like before. But as we mentioned before, x is equal to 0 is a singularity, so don't plug in 0. We lose information there. Even if it looks like the equation might work, please don't. So, in this, number 1, we only did 1, but they all follow that basic term. Solve your decimal equation for r. So r is equal to 1, 1/2, and whatnot. There are special cases for values when r, when it works. The general rule of thumb that you're going to need to work with is you work with a higher r value and then the lower r value. There are different cases when that's not the case. If they differ by a positive, when they differ by a positive integer, for example, repeated roots and the like. So please be careful. But so far we've dealt with only one example, but you're going to be dealing with simpler type equations. Notice we also focused on x is equal to 0 as a case. This theory still works. It'll be more messy, but it still works. It just, instead of x to the n and x to the r, it's x minus x naught to the r and x minus x naught to the r. Repeated roots, just like before when we dealt in when we were dealing with repeated roots in Euler type equations, you multiply by natural log x. But in a lot of these cases, just to be on the safe side, complex value stuff still works the same way as before, but you're going to be dealing with some of the easier stuff and more straightforward stuff. Hope this helps. Please let me know if you need a better explanation of stuff in the future. Have a great day.